I'm delighted, Kausik Lakkaraju has stepped in to take today's seminar. Kausik and others had from Dr. Biplov Srivastava's team had given a tutorial on this topic. I felt the topic was very interesting, and I think both the rating of AI system is an interesting issue, but it brings up a lot of broad issues that would be, I think, interesting to you. And the evaluation also is something that will be interesting. It's good to be aware of the ways things are evaluated. Many of you who do research would ultimately have to evaluate your systems, and they are very, very, depending upon the subject and topic and, sub area, you'll have to do different kinds of evaluation. Here, I think as this one is about evaluating and rating, I think we might learn something interesting. So this would be interesting. Kausik, take over.
Thank you for the introduction, Dr. Sheth. So good afternoon, everyone. Today I'll be talking about on this topic, evaluating and rating AI systems for trust through a causal lens. I'll be explaining each of these terms in detail, of course. So we'll start off by talking about AI and trust, and then we'll look at white box and black box rating. Okay, let me actually, Harshil, can you probably get that out of the way?
I think it's on your screen.
I don't think so. No, it's probably there.
Oh yeah.
You can maybe minimize the person, or maybe if you want to see the audience, you can just probably move it to bottom.
I think this should be okay.
Yeah, that should be. So we'll be starting off by talking about AI and trust issues in AI. And then we'll go in white box and black box rating, how we evaluate both of these different kind of AI systems. Then we'll be talking about the data and methods that we have used for this approach. And then I'll be giving you a brief demonstration of the tool that we built that you could use to actually evaluate these or rate these AI systems for robustness. And then we'll end by just having a Q&A session if you don't have any questions. So first, coming to AI and trust. So if we want to classify different kinds of systems, then we could say that there are learning-based systems, then there are rule-based systems. And learning-based systems mostly learn from the data. Typically, they learn correlations, and they look at hidden patterns in the data. And most of these systems are flexible. It is the ones that are being trained and built now, and they can handle any kind of uncertainty. Rule-based can be something that's based on reasoning, planning, scheduling, or optimization. But there are limitations for especially these learning-based approaches. One thing is they only learn correlations between the data, but they won't learn any causal concepts. So we'll be talking about that more in detail later. And there is a question of robustness and resilience as well. And also the resource efficiency, contextual awareness, and whether they can be generalized to other kinds of tasks, and so on. Then we have AI ethics issues. We have the overall trust issue, which is a very big umbrella under which we have fairness, robustness, again, lack of explainability, causality, and also lack of transparency in the systems. So these can be considered as the different components of trust. One is competence. Is the AI doing what it is supposed to do, what it is trained on, the task itself efficiently, and whether these are reliable under different conditions. Is it producing reliable output? And whether it upholds human values, whether it is fairly built and ethically being used. And does it actually allow proper human-technology interaction through explainability or more transparency? And how does the system actually give its result, in what form? So again, on the right side, you can see some of the examples, different AI systems, well-known AI systems, and also a check set of these different components, whether these are present or these can be applied or not. In some cases, you can see that yes, say for example, if you take maybe word tag cloud, it does what it has to, and it is reliable, and it allows human interaction. You can interact with the graph or whatever you see the word tag cloud. But whether it upholds human values or not, that is questionable. And if you consider self-driving car, everything about it is questionable, right? So it's not reliable. It might not be able to follow some traffic rules certain times when it cannot recognize, say, stop sign or something. So bias is very well known in the literature. There are now a lot of papers, especially with the rise in LLM's foundation models. You can see a lot of more bias issues in these AI systems. And in the interest of time, I might not show you a demonstration of this tool that we built. It's another tool that we built. It just will actually demonstrate the problem with specific AI systems called sentiment analysis systems, which give sentiment based on a given input text. Say you're saying that my uncle is feeling sad. Probably it will assign a sentiment score of -1. So it will show you, this is actually a screenshot that I took from the tool result output. Say, for example, you are considering different sorts of systems. On the top, you can see text blob, CNN, Distilbert, GRU, and so on. And you can see for sentences containing male attribute and female attribute. Say, my uncle is feeling happy, my aunt is feeling happy. So ideally, for any variation in the sentence, the sentiment should be the same. So the sentiment it is giving should be based on the emotion word, whether it is happy or sad. It shouldn't be based on the gender, right? So for text blob system, you can see that it has like completely merged with the male and female, both are almost the same. But for another example, you see over here, which is GRU, you can see that because this is a learning-based system, so you can see some discrepancy across both the genders. And again, instability of AI is also well recorded. There is a lot of instability in these AI systems. So our overall idea for this entire topic on rating is how we can develop automated methods to rate AI systems that can be used for communicating this trust in a black box setting. What if I can communicate the behavior of these AI systems to end users easily? So one way to do it is probably transparency through documentation. So everything is well documented, you know the outcome, you know the process, and you know who the producer, consumer, and also all the independent third parties that are involved are. So to give you one example, which is kind of similar to this kind of rating that we did, it's building trust via food labeling. Say you go to some kind of grocery store and you pick up like some noodles or something, and you just look at its nutritional info on the back, right? So you know how many calories does it have, carbohydrates, net carbs, fiber, all sorts of things that you're concerned about. So it's pretty much transparent. So you can consider this rating to be sort of like that. So you take an AI system, you know how it's going to behave for different kinds of data that you give, and under what conditions these can be applied and so on. Now I'll go to the next topic, which is on black box and white box rating. So before going into the actual concept, I'll tell you like a small story of this horse called Hans. So it's from 1900s in Germany. There is this horse called Hans, which was called as Clever Hans, because it could solve mathematical problems and it could read and also even tell time, or so it seemed. Turns out Hans had more difficulty answering the question when its owner wasn't around, or maybe when the owner did not know the answer to the question. So why is that? So it turns out Hans was actually picking up on subtle cues from his owner's body language and not exactly solving problems. So it cannot understand what 2 + 3 is. But say, for example, if I'm asking someone a question, and if I say that, like if I ask a question and if you're almost like coming at the right answer, you'll see some change in my body language and expression. So that's what was happening back then. So everyone thought like, oh, this is a very smart horse. It could like solve mathematical equations, read passages and stuff. So just like Hans, AI systems can sometimes learn patterns that are really aren't about intelligence, but rather unintentional human biases or signals that the humans give unintentionally. So it might not know what 2 + 3 is, but from learning its patterns and correlations, it might still be able to like give the answer. So the Clever Hans effect, it teaches us something. What it does is it reminds us that always question how the answer is derived, whether it's a horse or an AI system. There's often more to the story than meets the eye. So now let's talk about black box AI models. A black box model in AI context of AI refers to a machine learning model that operates as an opaque system. It's not at all transparent, where the internal workings of the model are not known and cannot be interpreted. So this lack of transparency makes it hard for users to detect the reason for potential biases or error that it is committing, or to hold the model accountable for its decisions. Again, another example could be like a self-driving car, like who is accountable when it hits some truck or so. So unbeknownst to the users, black box models can arrive at right conclusions, but for the wrong reasons, like clever hands. Again, some of the examples in this black box AI models can be deep neural networks and support vector machines. And coming to white box AI, it's called the crystal ball of transparent AI. So they are designed to be transparent and interpretable and allows users to understand how decisions are being made in the system. So unlike these black box, which operate as opaque systems, they are more transparent and they'll give you clear insights into the decision-making process. For example, maybe if you consider finance as a domain, white box AI models enable stakeholders like banks and investment firms to validate decision-making process, and it also ensures fairness and accountability. Some of these examples can be decision trees, logistic regression, all the early machine learning models that we learned about before. So there is this also a known trade-off that can probably be, that is applicable to most of the systems. So this is a very neat representation of it. So you can see that as accuracy increases, the interpretability actually decreases. You'll see that the model is being very, very accurate, but you don't know, you cannot even interpret its behavior. You don't know why you're seeing like a particular output. So if you look at this problem from like a software testing perspective in software engineering, a black box testing can be when you are giving an input and you don't know the internals of the model, you don't know anything about the model, you're just getting the output and you're trying to just do like some kind of evaluation just based on these two. When it comes to white box testing, you know the internal source code. You'll be like testing as a developer rather than as a user because you know the internals, and you'll be again passing the input, getting the output, but you'll have some internal knowledge as well as why like certain output was produced by the machine. So how can rating be used? How is it helpful? How can it solve this task of, or probably the problem of lack of transparency in AI systems? Say, for example, consider this company called, let's name it ABC company. And there's this guy called John who works for Household Essentials company and tries to analyze different customer reviews as a part of his job. So he realizes that segregating and analyzing each of these reviews manually can be a tedious job. So what he does is he just prepares a CSV file with user information. They have, say, IDs, and it will have, say, like sensitive attributes like gender and age, and also the exact review of the product. So one of John's friends suggested that he can probably use a sentiment analyzing tool that will give you like sentiment of each of these reviews, so that it will be easy to know like what the tone of the reviewer is and what exactly their opinion is on the particular product, just automating things. So John found that there are many such tools at his disposal, and he could not decide which one to use based on the data at hand. So if John uses our rating system, so because that would help users understand which system to use for an application for your own task. So John was able to pick up the right tool for his model, and he was happy with his final report. So one example can be, you can see this image over here. Say you have a system XYZ, you have a system LM, and we give these ratings with respect to gender when you have gender as protected attribute present in your data. So this is how the system behaves, and this is the comparison. So this is a promising idea that was proposed of how third-party assessment of models and ratings can help users make informed decisions without access to methods, code, or training data. So in the context of black box models, as testing is even more difficult, this is what our rating will help with. And rating methods evaluate AI systems with respect to bias, or can be just overall robustness that these systems exhibit. So on the right side, you can see, I'll be again talking about some metrics and stuff, but this is how the overall rating output looks like. You'll be able to see some scores over there under the partial order that quantify these effects or biases that the system exhibits or the robustness. And you'll see a complete order, which is just the final ratings given by the system that will allow you to compare across different systems. So what's the problem with the existing methods though that are being used to actually assess this fairness? So many statistical based approaches were used before to assess the trustworthiness of these AI systems, such as machine translators and chatbots. And there were works that did that. And there were also works that were produced on rating, which were again on causality. So I'll tell you about what this rating is from again another different perspective to get more a better understanding of the problem or of the solution rather. So say for example there is a self-driving car, right, that looks at the stop sign. But say someone actually intentionally went and added this small white dot that you see on the top over there, right? Just a small white dot. Let's call this noise as delta, right? So this is our self-driving car, which was trained. So, okay, it probably says that it is stop sign. It doesn't disrupt the system. So this is what is called as robustness certification. So it ensures that the model's decisions does not change within a certified radius R. So as long as your delta that you take is less than or equal to that particular radius, that particular value R, the system is not going to be disrupted. Otherwise, even a small dot can disrupt the entire system and it can just hit another car or something. So there is again the concept of verification. Okay, let's take the same example. So what verification does is, it will exactly determine what the value of R is, what exactly the radius is. So our rating method is similar to verification. So we are quantifying the behavior of the system and we are communicating it to the end user so that they'll be able to know, okay, this is how the system behaves. So it actually, our rating also evaluates the impact of each attribute on the system's outcome under different conditions. So for example, you can consider this as one perturbation condition where you are adding just a small dot, you are changing one pixel. Okay, now I'll be talking about data and methods. So this in here, I'll be explaining about the exact rating method and how causality can be used. So what is causality? Causality is the science of cause and effect. So I can give you like a simple example. Say if I go and ask you to like touch some hot object that is very hot, you won't go and touch it because you know that touching a hot surfaced object with hot surface, it can actually burn your hand. So that's simply cause and effect, causality, right? So this can be represented as using this particular causal diagram that you see over here. So they are nothing but directed graphs that give the relationship between causes and effects in a system. So the arrowhead direction that you see from X to Y, input to output, it shows the causal direction from cause to effect. Now I'll give you a little more complex example. Say there is like a protected attribute. Protected attribute can be a sensitive information about user. It can be their gender or race or age, if you consider that as a protected attribute. And there's an input and output for an AI system, of course. And if protected attribute acts as a common cause, so it is causing both X and it is causing both X and Y, then this can lead to what is called as spurious correlation between X and Y. So if you want to identify the exact effect that X has on Y, you won't be able to find it because there is a confounder involved. There is a protected attribute in the play. Okay, so this is called as confounding effect. And Z here, the protected attribute, is called as a confounder. And the path that you see from X to Y, so you can see a straight path, which is what we expect in systems. That is what machine learning models learn. They think that, okay, X causes, there is a correlation between X and Y, and that's it. Right. So, but if you also take into consideration this Z over there is another path from X to Y through Z. So that goes like all the way from here to here because of this confounding. So now you have two paths, one going straight and one going through Z. So this other path is called backdoor path, and it is completely undesirable in any AI system. And the machine learning models won't be able to identify it. It is the ones that are being trained today. So various backdoor adjustment techniques can be used to remove backdoor effect. There is like a whole lot of literature on how we can remove this backdoor effect to remove this effect of confounder. So the red arrow here indicates that this is an undesirable causal path, right? So I talked about another example as well before. You do not want a person's gender or race to actually affect an AI system, right? That's completely undesirable no matter what. And the question mark here denotes that these validity of these causal links have to be tested. So say if I'm considering like an AI system, and if I say that, okay, this is my causal model, and I'll just say, okay, this affects this and so on. So you can be a little suspicious about this, right? So we cannot be sure about this. We cannot say for sure this affects this in a system. So instead of assuming, what we do is we come up with certain metrics. I'll be talking about this soon. In order to validate each of these causal links that you see in the diagram and also quantify how strong is this effect of one attribute on another. So now talking about the metrics. So we perform both statistical and causality based tests to quantify the strength of the effects of each causal link. So the first one we'll be talking about is a very simple statistical metric. It's called weighted rejection score. So it just measures the impact of protected attribute on the output when there is no confounding effect or anything involved. You just want to see how age or race or gender is affecting an AI system outcome. That's it. It's as simple as that. So the corresponding causal diagram can look like this. Just forget that there is an input. You're only concerned about whether it is giving a fair decision or not. So we just compare, as I said, the distribution of output given protected attribute across different groups of protected attribute, across different races, different genders. And we use statistical students t-test to compare these distributions. We see how similar these distributions are or how far away they are from each other. So this is the t value over you see here is part of the, again, the students t-test. So we select 3 confidence intervals under which we try to validate these causal links. So these are 95, 70, and 60, but you can choose whatever you want, of course. And we each of these t-tests again have a corresponding weights that we assign. So that is represented by Wi over here. Say, for example, 95 confidence interval is a very high confidence interval, right? So if you're doing any rejections under that confidence interval, you'll assign more weight naturally. And as these confidence intervals decrease, you assign lesser weight to it. And you sum up everything, you'll end up getting weighted rejection score, which measures statistical bias. And the second one metric is called deconfounding impact estimation. Say now you have confounded, you have the confounding effect, you have this backdoor path which is undesirable. What are we going to know? So there is this backdoor adjustment method that I mentioned before. So the formula to remove it is denoted by this P probability of y given do of x. So the do here represents, do here is an operator that will remove this confounding effect. So this die percentage calculates the relative difference between the actual original distribution where you do not consider confounder at all, and where you perform this intervention. You are applying this do operator and you are just doing a relative difference between both these. So with confounding effect, without confounding effect, what is the difference? So that you'll know the impact of confounder, right, on the overall system output. So this is again the metrics mathematical formulation for it, with and without do operator, as I said, and you just multiply it by 100, you'll get the percentage value. Then this is a variation of a known metric in the literature of causality, at least, where they talk about something called average treatment effect. Say in the example that I talked about on the stop sign, you want to assess. So if after I add like a small dot, change a small pixel on the image, what kind of effect does it have on the outcome? How do I quantify this effect? Effect of the perturbation or effect of treatment? So we just took this average treatment effect metric from causality literature, and we modified this metric to measure the impact of the perturbation. Here we are considering this perturbation to be the treatment. So it's like treating a patient, right? You just give a tablet and you'll observe how the patient is doing across like some different days. So this is more simpler. You just measure, say, I'm giving like certain treatment or I'm making certain perturbation. I'm adding this white dot to the image. Then I'm measuring the y given do of p. And then before adding this white dot to the image on the original image itself, I'm computing the interventional distribution. Again, y given do of p equals to 0. So no treatment and any treatment, and you're just measuring the difference between these two distributions. So then we came up with another metric to improve on the original die percentage. So the original die percentage that was proposed, it only works on like assumes a linear relationship between attributes. So in this one, without making that assumption, we just tried to compute the difference between the average perturbation effect before and after the confounder is involved. So it again measures, the measurement is similar to dye, but just the method changes. So it will still quantify the effect of confounder on the overall system outcome. So this can be considered as confounding bias. So far, we have looked at statistical bias, and this is confounding bias. And then we talked about the effect that perturbation has on the outcome of an AI system. So how does this, if we talk about rating workflow, then it can be considered or split into two different parts. One where you're trying to give an input, you have an input data with you, and you will get predictions, right? So how are we going to do it? So you can have, data that has only text or only image or numerical or multi-model data. And you're pre-processing data if it is necessary, and you're applying these different perturbations to the data. And you're setting up your test systems. It can be a pre-trained AI system that can be again unimodal, multimodal based on your data. And you obtain the predictions from the model. Say now you have all these ready. You have your input, you have your predictions that you came up with. And now whatever rating workflow actually does is, as the algorithm starts, it will check if it has any protected or sensitive features, age, gender, or whether these are present or not. And if they are present, and then what we do is, if that protected attribute is acting as a confounder or not. If no, then the bias is simply statistical. Okay, we calculate weighted rejection score that I already talked about. And we compute what is called as partial order, which will quantify the statistical bias. And you compute the final ratings. That will tell you, okay, you can get a comparison of how systems are doing in terms of statistical bias. And you stop the algorithm. So you do not have any protected attributes. So our rating method doesn't really focus on that. If you do not have any protected attributes, then you're not interested in knowing effect of different attributes on the outcome. So it simply stops the algorithm. It just assigns a score of 0 to everything. But say you have a confounder involved, then you can again use this bunch of other metrics that I talked about. One is average perturbation effect that measures the effect of perturbation. And then we have pi or dye percentage that quantify the confounding bias, the second kind of bias we talked about. So now I'll get to the interesting part where I'm going to give you a demonstration of a tool that we built. So if you want to try it out, there is this, I think it only has link to the video that we have, but anyways, I'll actually give you the link to the slides as well later on, but I'll show you the actual tool right now. And so this is our tool. It's just called ARC, AI rating through causality. So once we click on proceed, there are 4 different tasks that you can test our method on. One is simple binary classification, and you can see each of the descriptions of these tasks pop up over here. So the interesting and most recent work we did was on evaluating time series forecasting models. I select that. And now it takes us to the data page. So we have used the stock prices data that is publicly available on Yahoo Finance that people use for forecasting typically. And then we only have one input and output in our data, but for protected attributes, you have a choice of choosing how many ever you want. So again, here industry and company, what does this actually denote? It denotes that whether the system is being biased based on the industry that we are choosing or company, whether it is predicting that making more errors when doing prediction for Meta compared to say something like Wells Fargo or maybe Pfizer, whether it is showing the discrimination across different companies and industries, like pharmaceutical versus tech companies or finance. So maybe we can choose both and see how it performs. So you can choose how many other systems you want. ARIMA is a statistical model. You can see a description over here that is widely used. It was, they used to use this model back in the olden days. And we have biased and random system, which are again baselines. Biased is intentionally we made it biased so that you'll know how extreme a system can go, how biased it can be. And then we have random system, which randomly forecasts the different values in a specific interval that we define. And then we have vision transformer based models, which are based on vision transformer architecture called Whitlam spec. Large was trained on large data set and small was trained on small data set. So you can also see a log of different options that you have chosen so far. And we just click on submit and proceed. Then we have 3 different metrics. I already covered these, right? So you can choose whatever you want. Say, for example, you want to know the confounding bias. We click on submit, it will take some time to process. So you can see the corresponding causal diagram over here. And you can see the log of options that we have chosen. And then the results are being displayed here in a tabular format. So on biased, you can see just fixed values because it was intentionally made biased, right? But for these different systems, you can see across different perturbations. So for ARIMA, you see a couple of null values over here because certain perturbations cannot be applied to it. Say, for example, you have some perturbations that are image specific. Those cannot be applied to a statistical model like ARIMA. So you see a bunch of null values over here. And again, these are just quantifying the biases that we see. And based on that, for again, each of these perturbations conditions, different conditions that we have, will give final ratings. For example, if you see this bias, you can see it is always at the end. It is always given a rating of 5. So rating of 5 denotes higher the rating, higher the bias. Lower the rating, lower the bias. So ARIMA is somewhere in the middle always. And you have transformer-based models which are performing relatively better compared to these other systems. I can show one simple task so that it will be easy to understand as well. So for example, there is this well-known dataset in finance called German credit dataset that contains information about 1,000 customers. And it has attributes like the age of the customer, the gender, their credit amount, and also the risk. So risk here is the outcome attribute. So it will tell you whether that it's a risky customer, that particular customer is risky or not, whether approving a loan or some kind of credit card to that person, whether it is risky or not. So in literature, this is known to be a completely biased data set with respect to gender and age. So now let's see if our tool will be able to reflect the same with our own metrics that we have come up. So you can choose gender, age. This time I'll probably choose just one attribute. So we only have two different systems. One is a logistic regression model, simpler model, and we have a random system that assigns like random outcome. So now let's look at a simple metric, maybe weighted rejection score, which will quantify the statistical bias. So it will directly tell you whether this predicted attribute actually, gender is actually affecting the risk or not. So turns out a random system is not at all biased because it's randomly assigning, right, based on nothing, to be honest. So logistic regression model, it is showing slight bias, so of 0.6, right? This is a quantification again. And you can see the final ratings given by our rating system. This is a more like a toy example or a smaller example so that the whole overall concept will be clear to you. So if you're interested, I also have a demonstration video over here that you can see. You can just scan and you can look at the demo video if you want to. But I'll be, again, as I said, sharing the slides as well. So we have discussed about the importance of building trustworthy AI systems, both black box and white box settings. We did not go deeper because it's actually harder to evaluate black box systems. You don't find white box systems these days, especially with these foundation models or large language models. They aren't transparent at all. You don't know how it behaves or why it produces a certain output. So we introduced rating more of from a certification verification perspective, which is very prominent in adversarial attacks kind of domain to promote trust. And I also discussed about data and methods used for rating AI systems. Then we looked at causality-based rating, and then I demonstrated the R2. So this is our perspective. So assessment and rating is an important approach to build trust with AI users. And there is, of course, more to be done because, as I have mentioned before, there are now a lot of foundation models, plenty, and it's hard to just assess these models. You don't know, their behavior is completely black box, right? And how we can also make use of multi-model data, because now you can use multi-model data on like any system. There are more multi-model models and more focus on more traction is towards those kind of systems. And how we can scale these methods to other types of AIs or other domains. So here on the right, if you scan this, you'll be able to find. So this is a part of a tutorial that we gave in collaboration with JP Morgan and Chase. So they have an AI research team who work on something similar. So they helped us with this, especially the time series forecasting task that you see. So we have also work on rating foundation models as well. So on the tutorial page, you can just find more information over there. You'll also find our slides deck over there. So right here, if you open this page, you'll be able to find it over here. So this has more information, by the way. This has, I think, 95 slides. So I just cut it down in the interest of time. So does anyone have any questions, or if you are interested to look at our other tool as well, I can do that. Or if anyone has any questions, I'll first take. Okay, I'd be happy to answer. Please. So I'll just quickly just show how the tool works. If you're interested, you can probably look at this tool as well. This is more easy to use. So say, for example, let's go to emotion by nouns. So you are giving like some sentences that has names, like something like maybe Amanda or Mary or John. John is feeling sad, John is feeling happy, those kind of names. So these names here can serve as a proxy for both gender and race of different users. And say you want to look at just text block, right? So you can see female text block. And how CNN, you can see that it is more unstable, right? The sentiment it is giving. And distillable slightly stable. So you can see more instability for learning-based models rather than just simple rule-based models. And you can also, of course, see for different emotion words again. LSTM, GRU, distillable. For this word called annoying, when you have this in your sentence, what kind of sentiment does these different systems assign? So yeah, I just wanted to show this so that you'll understand the problem of the overall bias, and that is even more actually known in the sentiment analysis systems and all other AI systems. Yeah, that's the end of my presentation.
No question, team? All right.